Hey everyone, welcome back to A View from Earth, the official podcast of the Fisk Planetarium here at CU Boulder. This is a show where we talk to local scientists and, of recent, more maybe even artists and potentially politicians about their work and kind of put a face to the kind of things that you're hearing about that are coming out of here at CU Boulder. So my name is Colin Sinclair. As always, I am an undergrad at CU. I study astrophysics and computer science, and I give presentations at the planetarium, especially when the building is open. These days, we do the podcast, which is a lot of fun, and I'm joined by my co-host, Tara Tomlinson. Hi, Tara.
Colin. Yeah, I'm Tara Tomlinson. I'm a CU alum and a planetary scientist, presenter at the planetarium. I also coordinate our outreach program and some other fun little Fisky things, including co-hosting this podcast,
Woohoo!
which is the best.
And we're also joined by our producer, John. Hi, John.
Hello.
Great. He mutes himself. Yep, that's it. Cool. Well, I think that this is a very interesting conversation that we had with Dr. Amanda Hendrix. There's a lot of stuff that I learned about planetary science, especially I had no idea that ultraviolet light was really such a gateway to understanding ocean worlds.
Yeah. Planetary science, especially, like, we make a lot of use of the visible spectrum and then the things right around it. So like IR and UV are kind of the big ones. We don't do so much with like X-rays and gamma rays, sometimes radar, but mostly like, I don't know why that spectrum, kind of that chunk in the middle, seems to be the most useful.
Well, and I'll throw this in for the reason that when I listened to space podcasts before I went to school, I was always confused by this. I didn't understand what it meant to, like, this whole idea of the spectrum until I learned about it. So I'll say really quick for those that are unclear, all of these other things, right? Ultraviolet and radio, and then on the other end, infrared. Well, I guess radio is on the far end. These are all basically colors of light that we can't see, right? It's just the same thing, right? It's the same thing. How blue is different from red, right? Radio is different from visible in the same way. So that's all that is we're just looking at different kinds of light that our eyes can't see. So hopefully that's clear for everyone that listens.
Yeah. It's super cool because different, like she was kind of saying, different kinds of light are good for detecting different kinds of things.
Right.
It's so cool. I think it's super cool. I'm biased, but I think it's awesome.
That's really, I feel like, the key to a lot of what astronomy has learned was recognizing, hey, we can use different kinds of light to kind of glean different kinds of information from different areas of space. Without that discovery, I think we'd still kind of be in the dark. We'd still kind of be in the dark. John, you could not look more unamused right now. We'd still kind of be, right? And now, I mean, all you need is basically a picture, right? It's a special, highly detailed picture, but it's, at the end of the day, it's just a picture, right? Mm-hmm. And you can, do all sorts of things with that.
Yeah, it's super fun.
The other thing I think that might be useful to mention is that, and I think we did mention this once or twice, almost everything we talked about was a moon of one of the outer four planets. That's almost all of these bodies, right? And Tara, you know a little bit about moons.
I know a little bit about moons, yeah. No, it is really interesting that these all happen to be moons. And, there's water and ice other places that's super weird, like the North Pole of Mercury. I think that's really cool. The planet closest to the sun has ice on it. What? But it's smaller than some of the moons out there.
Yeah, true.
Yeah, it's just, I think it's mostly just the specific set of conditions that these moons are under with, they're giant planets. There's tidal heating that's pulling them in different directions. And, ice is an excellent insulator. And so any warmth that it has in the inside is going to be helped to hold in with these giant ice layers. Yeah, that's part of the reason why I think moons are so freaking cool. Is because there's so much weird stuff going on and all of these ocean worlds.
Well, hey, what do you say we jump into our interview then?
I think that sounds great. All right, so today we are talking with Dr. Amanda Hendrix, who is a CU alumnus and a planetary scientist known for her pioneering studies of solar system bodies at ultraviolet wavelengths. She was co-investigator on the Cassini and Galileo UVS instruments, is a participating scientist on the Lunar Reconnaissance Orbiter LAMP instrument, and is a principal investigator on the Hubble Space Telescope observing programs. She's also co-lead of NASA's Roadmaps to Ocean Worlds group, advocating for exploration of ocean worlds in the outer solar system. She's also a NASA astronaut candidate finalist in 2000. So Dr. Hendrix, thank you so much for joining us today.
Hi, thanks for having me.
Yeah,
it's fun to be here.
Awesome. So for starters, obviously from that bio and your Wikipedia page, they described you as a pioneering studies of solar system bodies at ultraviolet wavelengths. So for our listeners who maybe aren't familiar with this, what does it mean to study bodies at UV wavelengths, and how does one become a pioneer in this field?
I didn't really know I was a pioneer, but that sounds good, I guess. So I kind of got into studying bodies in the solar system in the UV as a grad student at CU. And, you know, traditionally UV wavelengths, which, you know, are those wavelengths shorter than visible wavelengths that our eyes can see. They're traditionally used to study atmospheres, mainly upper atmospheres and aurora. And, you know, like they've been used a lot to study Jupiter's aurora, Saturn's upper atmosphere, the Mars atmosphere. And as a grad student, I got interested in the idea of using UV wavelengths to study surfaces more than atmospheres. I've always just kind of been interested in, or I had gotten interested in moons in the solar system, which typically don't have atmospheres, including Earth's moon. And so, and I got involved in the Galileo ultraviolet spectrometer team as a grad student, which was really great. And I feel very fortunate to have gotten involved with them. And so I was kind of assigned to working on the moon data from the Earth moon flybys of the Galileo spacecraft. And so I got interested in, well, how does the UV light interact with the regolith, the grains of the surface? And what does that tell us about the composition and the properties of the regolith and how the surface has evolved? Because, you know, on a body like the moon, it does not have an atmosphere to speak of. It does not have any shielding from all these processes that bombard the surface, like micrometeoroids and solar wind. And so it evolves with time. And so I got interested in how does the surface evolve, and how can we see that and sense that in the UV. So, and it kind of started from there. And then I kind of got into looking at the Galilean moons, the icy moons now with UV wavelengths, again, during the Galileo mission, and then Saturnian satellites and asteroids. So, so it's been a fun project. And I guess the thing is that, you know, I certainly was not the first person to look at surfaces in the UV, but it wasn't done very much at that time. And so, and I have kind of stuck with that as kind of my thing. So maybe that's why it says that on the page. So anyway.
Yeah. So is UV, would you say it's an maybe advantageous way to look at surfaces in ocean world? What makes UV so helpful or special, or why UV?
So I feel like different wavelength regions have different benefits. In the UV in particular, those wavelengths, you know, you can think of it as the sunlight coming into the regolith, or the icy regolith, or silicate rich regolith, whatever you're talking about. The sunlight coming in, and then what we're measuring is the reflected light coming out. And that light has not gotten very deep into the surface. Whereas at longer wavelengths, the light will get in deeper and then it will come out, and you will be probing deeper into the regolith. But in the UV, you're just sensing the topmost grains. And so I usually like to think of it as being quite sensitive to these weathering effects that I was talking about, and also being complementary to the longer wavelengths that are probing deeper. Also, there are particular minerals and ices that have diagnostic spectral features in the UV, and they don't appear at longer wavelengths. And the same is true for infrared wavelengths, for instance. You can detect things there that you can't detect in the UV, but the same goes for the UV. You can detect some things there that you can't detect at longer wavelengths. So they're really quite complementary.
Would it be appropriate to say that using different wavelengths, for your how you're looking at objects, kind of is like a variable depth mirror, far further into the surface? So your shorter wavelengths, like you said, are just right on the surface, and then we can go deeper.
Yes, I think that's a good analogy, and I think that that's a good lesson, kind of, for thinking about planning payloads for future missions. I think it's really important to cover the entire wavelength range as much as you can, so that you can probe different depths and also get different compositions by going after different diagnostic spectral features, like absorption features and emission features.
Sure. Okay, so kind of turning. Oh, sorry, Tara. Did you want to add something before I shifted gears?
Oh, no, I was just thinking that it would probably be super helpful for like confirmation of spectral features. Like if I find something in infrared, and spectroscopy is kind of black magic sometimes. I don't exactly know that that's what I'm looking at. So to have confirmation in the UV too.
Yes,
like
and you can do that. Helpful. And as a matter of fact, we did that for Europa. And Europa, this was back in the Galileo mission, and the infrared instrument was sensing a little feature that they thought might be due to hydrogen peroxide, H2O2. And so they came to us on the UVS team and said, hey, do you think you can measure H2O2 in the UV and confirm what we're seeing? And we could. There is the diagnostic spectral shape in the UV of hydrogen peroxide, and we were able to find that on Europa and confirm what the infrared instrument was seeing. And that's an important species on the surface of Europa there. So that was a nice example, I think, of that kind of confirmation that we can do sometimes with a couple of instruments.
So speaking of, kind of what you use this technology to look at, ocean worlds, I'm curious, what exactly does it take for something to qualify as an ocean world?
Oh, right. Good question. Well, we did this study recently called Roadmaps to Ocean Worlds. And this is something where we looked at, what should the kind of near-term, midterm, and kind of long-term plan be for making an ocean worlds program at NASA, mostly. And as part of that, we thought, okay, what is an ocean world? First, we have to figure out what we're talking about. And, there might be a couple different, definitions floating around out there. So what we decided that we were calling an ocean world is a world. And in that study, we focused on our solar system. You can imagine there's probably ocean worlds and other solar systems too, but we're just focusing on our solar system. And an ocean world is defined as a body that has a subsurface ocean or a surface ocean. Really, Earth is an ocean world, of course. Earth is the original. But mainly a subsurface ocean is what we're talking about. It does not have to be a global ocean, but it does need to be currently liquid. Because we do have evidence for some worlds in our solar system that have passed ocean world, they have passed subsurface or surface oceans. But for our study, we wanted it to be current oceans, currently liquid under the surface. And so you might ask, which are those ocean worlds?
Yeah, right. Well, so I was curious. So ocean world, this is the term you're using in your study. Is that the technical term to describe ocean worlds?
Yes.
That's great.
I think it is.
We often congratulate astronomy for calling things what they are, and instead of
around the bush.
Yeah, right. It's an ocean world. Done. That's it. So yeah. So you're right. Yeah. Of course, we all have this list of questions here. So how many do we know of right now? And I'm curious, How do you find those and then be confident that they are in fact ocean worlds and add them to the count?
Right. Really good questions. Okay, so the ones that we know about now that we kind of think of as known or confirmed ocean worlds, first there's Europa. That was the first detected ocean world in our solar system. And then there's Enceladus, Titan, Ganymede, and Callisto. I think I've got them all. Those are the known ocean worlds. And then we've got some possibilities out there too. And these are the ones that we kind of want to go after. They've got some hints and we want to kind of go after them and see, are they really, can we call them confirmed ocean worlds once we confirm a few things? And that's like Triton is a good candidate. Pluto, Dione, Ceres, even. Ceres is, kind of, it's an asteroid, but it's also a dwarf planet. And that may be an ocean world too. It might be kind of an N-member ocean world is how I normally think of it. So those are some of the candidate ocean worlds out there. And so what we need to do, there's a few ways to actually find out if they are ocean worlds. A few signatures that you can think about, but you also want to think about also if these bodies have the energy to sustain a liquid ocean. And sometimes you can think of a situation where a body has kind of leftover or remnant heating in the interior from formation, remnant radiogenic heating, that it might sometimes be enough to sustain a liquid subsurface ocean. Or there might be a lot of gravitational energy. This is probably mainly the situation for Europa and Enceladus, where there's a lot of gravitational interactions with the parent planet and other moons, constantly tugging on it and keeping the interior at a warm enough level anyway to maintain an ocean. And also you can think about if there's tidal energy, can the body actually convert that into heat? Sometimes depending on the makeup of the body, it won't do anything with that tidal energy and it won't be able to maintain an ocean. So then we can go and visit these bodies and see, are there actually kind of hints that there is geologic activity that is indicative of an ocean. So you might look for hot spots on the surface. For instance, at Enceladus, we saw a big hot spot at the South Pole. Now we saw that kind of simultaneously with the detection of the plume. But that was a big giveaway that yes, this plume is real and it's localized at the South Pole. And the hot spot wasn't actually really hot, but it was locally hot compared to the temperature of the rest of the surface. You might look for volcanoes or tectonic activity. You might look and this was kind of a clue also on Enceladus, for crater-free areas. So from Voyager imaging, we knew that at least at that resolution, there were these vast areas that appeared to not have any craters on them. And so for an airless body hanging out for billions of years in the solar system, you'd think it would accumulate some craters. But if there's crater-free areas, then that indicates probably some sort of resurfacing, which might be due to a subsurface ocean. And then you can also think about surface composition, and is that kind of consistent with maybe having a subsurface ocean? And here was a fun one at Titan. Titan's different because it has a subsurface ocean and it has liquids on the surface, right? It's got those surface lakes. But that was one where we were able to actually see a specular reflection from that liquid on the surface, which is kind of a sure thing that it's liquid. But that's another thing, if there were a surface liquid, you would look for a specular reflection to confirm that. And I know another one is an electromagnetic response. And this was kind of a big clue at Europa, because we found that Europa has this induced magnetic field because it's sitting in the larger Jovian magnetic field, and it's got a conducting layer, which is the salty subsurface ocean. And so that the interaction between that Jupiter magnetic field, and it's kind of wobbling because the orientation of the field is offset from the spin angle of the spin pole, I should say, of the planet. So it kind of wobbles. And so Europa is sitting in there in this wobbly, moving magnetic field. And so it's perfect for kind of detecting if there is a conducting layer like a salty ocean in there. And that was different from the situation at Enceladus, where it would have been nice if Saturn's magnetic field were tilted an offset from its spin pole, but it's not. So we couldn't really do that trick with Enceladus to try to detect the subsurface ocean. So we had to use other techniques there. But luckily Enceladus is sort of shouting it out at us. I've got a subsurface ocean with the plumes.
So it sounds like you really have a large bank of tools to draw from, you know.
Well,
given any situation, you could say, okay, well, this applies and this applies and this applies to all of these.
Right. And ideally, you'd want to have like a couple of those boxes checked, you know, just to make sure. Sometimes if there's only one, you might still kind of want another confirmation just to be double
sure.
But
yeah, you got to have your evidence.
Yep.
So I think we touched on this a little bit. Maybe it's just my own previous astronomical knowledge. So I'll ask this question anyways. For ocean worlds, I guess the better way to say this is, are there ocean worlds whose ocean is not made of water, right? On Earth, we have a water ocean, but other things can be liquid too. So I wonder.
Other things can be liquid, and we had some debate in the Roadmaps to Ocean World group whether Io should be considered an ocean world, because it's got a magma ocean, right? It's hardly water, but it is kind of liquid. But we actually kind of decided, that's maybe we need to draw the line somewhere. So technically we're not really calling Io an ocean world, although one could consider it maybe an end member. But we do not have the word water, I don't think, in our definition of ocean world. But typically that's what we're looking for. Actually, I mean, a lot of these ocean world studies are going after, is there life? Because, you know, as for life as we know it, we need liquid water. And so that's kind of, you know, really where a lot of these studies are going in terms of ocean world, is looking for life.
So you're telling me we don't expect to find life in a liquid magma ocean, unfortunately?
Not life as we know it. That would be one of those wacky kinds.
I understand.
So we've talked about some of these cases, Europa, Enceladus, Triton, all of this stuff. Why is it that most of these ocean worlds are in the outer solar system? Why don't we find some closer in?
Well, that's a good question. You know, and I would say that the main reason is because most of the water is in the outer solar system, right? And that's probably because of how the solar system formed and the temperature gradient, and the temperature gradient with things mainly being warmer in the inner solar system. And so what you've got is liquid water on Earth on the surface, frozen water on Earth's surface only in the coldest regions, and frozen water in only the coldest regions in the inner solar system, like at Mercury's poles and the moon's poles. But then out in the outer solar system, where things are in current day still cold enough to maintain, for water to be stable as a solid, just because things get colder as you go out farther from the sun, and probably around 5 AU is where that really starts to happen, out at Jupiter's orbit. That's where you've got a lot of frozen water, and where there was a lot of water present even early in the solar system, you know, from there on out to farther heliocentric distances. And so that's where it's kind of natural for ocean worlds to mainly still exist today. And you can also think about things like, well, these are all moons, pretty much, right? Forget about Ceres for a second, but all of these other ones are moons. And so they have, generally speaking, you know, an energy source, a potential energy source, which is gravitational interaction with a giant planet that it's orbiting, and other moons that are providing additional tidal input. And so those factors kind of are the main reasons, in my mind, off the top of my head, for why, you know, you've got these ocean worlds mainly in the outer solar system. And it kind of shifts. We had thought in looking for life in different solar systems about looking for rocky worlds that are like Earth, but maybe, this has kind of expanded that, traditional Goldilocks zone that everybody talks about being, in the something like 1AU kind of rocky terrestrial planet area. Move it out maybe to where you might find more ocean worlds with icy worlds with subsurface oceans, if that's the kind of life you're going after.
Yeah, because if you look at the charts of like our Goldilocks zone, it basically stops at Mars, but we're looking for life way past that.
Right. It's like the Goldilocks zone has kind of grown in the last couple of decades.
Yeah, it's a good starting place, but you got to look further than that.
It's interesting. In my astronomy classes, we simultaneously acknowledged the idea of a Goldilocks zone and kind of struck it down all in one discussion because of this very reason that, hey, there's liquid water way beyond the Goldilocks zone. So what does it even mean? Yeah. So I'm curious, this is just a personal experience question. So you were the co-investigator as we talked about earlier, on the Cassini and Galileo missions, which helped us study and understand some of the first candidate ocean worlds at all, like Europa, Ganymede, and Enceladus. And as you've mentioned, that oceans had been hinted at on these bodies from the Voyager missions. But I'm just curious, what was it like for you as someone who studies these things and is excited about them to see confirmation of things like Enceladus's plumes to come down in the data?
Oh, it's so exciting. So exciting. Especially, I have to say, the whole Europa thing was very exciting, but that was a little slower in coming. And Europa is, I'm not dissing Europa at all. It is very cool, but it does not have active plumes, like going off in our face practically. So the Enceladus makes it a lot kind of easier for us to like go, wow, oh my God. And so, being around, being on the mission, being involved in looking at data when that discovery was made was so exciting. Oh, I mean, that was definitely a whole career highlight thing. And especially because, you know what, I wanted to tell you that, because we were talking about ultraviolet wavelengths and what you can do with them and everything. And one of the things that we were doing on the Cassini mission with the UV instrument, and I'll acknowledge my friend and colleague Candy Hansen, who really kind of led the effort on the team. She kind of led the effort to do these stellar occultations with the UV instrument. And that's where we watch the star pass behind the body, and we're observing the spectrum of the star, and we see if it kind of dims as it approaches the limb, which we would expect if an atmosphere is present. And then as it goes behind the body, we don't see the star anymore. Signal totally drops out. And then when it comes out on the other side, maybe we'll see a dim signal, and then it brightens and brightens if there's an atmosphere. So we did that experiment a couple of times at Enceladus because we thought maybe there's an atmosphere there. And in the UV, this is a particularly sensitive place to do this. Getting back to the UV, because you can sense water absorption, you can sense CO2 absorption if CO2 gas were present, and at detectable amounts, and other kind of candidate molecules. And so we did the experiment. We did not see any atmosphere. We watched the star, and this signal stayed very bright and then dropped like a rock as it went behind the body. And that experiment had been done early in the mission, and it was at kind of equatorial latitudes. And so we thought, okay, well, Enceladus doesn't have an atmosphere. And honestly, why would it? It's like a really tiny icy body. No, so, okay, we did the experiment, but we naturally had a couple of those experiments in the plan. And I think it was the third time we tried it. We happened to be watching the star pass behind the South Pole. And sure enough, the star went behind the South Pole, and then it came out up at northern latitudes. And there's an atmosphere at the South Pole and not at the North Pole. And we're like, okay, that's like a localized atmosphere. And that happened to be the same flyby where, the cosmic dust analyzer measured the dust, ice particles associated with the plume, and the couple of the other in situ measurements were made to measure water vapor in situ, and that's when the hotspot was detected. So it all kind of came together at the same time in a very exciting way. So everybody kind of came into work the next day, and we all kind of met together and talked. What did you guys detect? What did you guys detect? And everybody kind of, it was like all these different pieces of the puzzle just kind of came together all at one time. So it was really exciting, really neat.
I'm curious about that last part, kind of the pace at which this excitement occurs. Something that's familiar, I think, probably for all of us, was the Perseverance landing that just happened a couple days ago, right? And there's this great footage of watching, the mission control room, and everyone just loses their minds as soon as they are confirmed that Perseverance safely landed on Mars, right? That's like a huge thing. How does what you are talking about compare to something like that? Is it something where you immediately see the data and or like do you have to talk with some other people first and then do you celebrate like that, or how does the pace compare?
Well, I'd say it's it kind of depends, but mostly I'd say it's usually a little bit slower than like landing a spacecraft successfully, just because you've got a data set, and I think sometimes you might look at it and go, oh my God, but then you're like, hang on, don't get too excited, let me just check and make sure I did the calibration right and everything, and then it kind of starts to build up more. And then if you're talking with somebody else from another instrument team and they're like, oh, I detected this, and they're consistent, then you're like, okay, this is big.
So for a spacecraft like Cassini or Galileo, you're not all necessarily in the same room when you receive this information, right? You could be at home or in your office somewhere separate from other people.
Right. And I seem to recall, this is my recollection, I think that this is right, is that I feel like the data from that Enceladus encounter came in maybe kind of overnight or over the weekend. But then we all came into our meeting that we had planned to have, like, okay, let's talk about how that flyby went. That might have been like on a Monday morning. I should go back and check what day that actually was. But I remember all being in the same room then, and everybody was like, oh my gosh, we found this, So it was just a matter of kind of, then how are we going to tell this story? And by the way, at that point, one of the other kind of interesting things was that we did not actually have images of the plume at that point, right? It was like all a little bit invisible, except for the hot spot. But, it was like a detection of gas, particles, and it wasn't like a regular, traditional image. There had been hints of a plume in images from earlier in the mission, but it was kind of like not really clear enough to make a firm case. And so everybody kind of didn't pay too much attention to them. But then after all of these other instruments detected signatures of the plume, then the camera was able to really figure out how to do the measurement properly. Because remember what like for instance, the UV instrument is looking at gas through a stellar occultation. And most of the images that you see are particles. And most of the images that you see are particles at high phase because they're very fine. So you have to look when the sun is back behind Enceladus. So the disk of Enceladus is dark, and then you're just looking at the kind of sunlight coming in through all of those grains and getting it's backlit. So anyway, so once we kind of figured all of that out, then, the images started coming in. And then, of course, we had to change the trajectory that we had planned out for, 4 years of science plans, got altered because then we wanted to keep flying by Enceladus and doing all of these observations. So anyway, this is very exciting.
I wonder, maybe this is kind of like a larger question, but how was the data released at that point, like getting out to press conferences and things. Like today,
Right.
you know, we have so much mass media, social media, online stuff that as soon as somebody even hints that they might have discovered something, it's like, oh, we found it. Like plumes on Europa. Somebody said, we
Right.
might have those. And of course, the media is like, there's plumes on Europa.
Right.
And everybody loses their mind.
Like,
And
hang
then we
on.
have to come back and be like, wait. But I think was it easier back then to kind of temper this excitement or keep people from just running with these discoveries that may or may not be actual discoveries?
Right. I think that the kind of common thinking, and this was probably stated or maybe even written down, but was that you know, for these big flybys where everybody knows we're looking for something, we might find something big, but you know, you're not supposed to just go off and blab it. You're certainly, when did Twitter become a big thing? I don't remember Twitter being a big thing in 2004 or 2005, but maybe it was. But nowadays, I think people say, don't tweet this yet, you know, obviously. Don't tweet it until we've got our story straight. And, you know, for most of these things are going to turn into science papers or nature papers. And so you're not supposed to really say anything because the journal wants you to keep things under wraps until the paper comes out. However, often there'll be like a press conference. Like I remember with that Enceladus discovery, you know, we knew it was big. And so one of the first things that we started talking about was, okay, how are we going to release this? We got to do a press conference, you know, within a couple of days. And what are we going to release right away? But I think that with these kinds of things, people kind of know, you know, nobody's going to tweet it out. Nobody's going to blow the story really, because, you know, we're all a team. Everybody's got a part to play. And so, especially on these big spacecraft missions.
So coming back to another thing that we kind of touched on, but of course, the thing that everyone always asks about these ocean worlds, how closely is the investigation of ocean worlds intertwined with astrobiology? Obviously, like you said, water is the place we're looking for life. And so what are some of like the big questions that we're trying to answer with regards to ocean worlds and astrobiology?
Right. So good question. So in our Roadmaps to Ocean Worlds group, we kind of set up a framework for, and I started talking about it a little bit with, the first step is to identify which bodies are ocean worlds actually. And we wanted to make kind of like a scheme, kind of a plan, because, you know, like we talked about, most of these bodies are out in the outer solar system. It takes a long time to get there. They're expensive. And so let's put together a plan so that we're all working together to go after these questions. So first you got to find the ocean worlds and confirm that they're ocean worlds. Then you want to characterize the ocean itself. And you want to characterize the ice ocean interfaces if you can. You want to characterize, you know, the salinity of the ocean. And then it's only kind of at the final step that you want to actually search for life. And that's harder to do. And there's a lot of work going on right now to actually be able to do that, you know, because it involves particular instrumentation. And that is particular to the body itself. You can imagine that you could design a mission to fly through the plumes of Enceladus and scoop up some of that material and hope that you are catching some dead bugs that are being ejected from the ocean through those jets. And then what do you do with them? You've got them on board. It's really hard to bring them back to Earth to measure in the lab, because that then ends up getting very expensive and risky. And then, you know, you've got planetary protection to think about and so forth. So then you have to think about, well, I've got to take along the proper instrumentation to find out, are these actually life? And that's very tricky and complicated. And when you're, because for all these missions, they get expensive, everything's mass constrained. And so you're talking about tiny instruments that need to do some very specialized measurements. So it's just very hard. And then you can think about, okay, well, then another option is to go land on Enceladus or land on Europa. And then you have to think about, well, we've got to choose the right landing site. We've got to land safely. And any site, say on Europa, where we might want to land to actually go after life is probably going to be like, I don't know, what if there's like plumes coming out, or it's really rocky. And so it's tricky to land there. And then again, you've got to have that instrumentation with you to be able to see if you're actually detecting life or not. And how do you detect it? Are you looking for something moving? Does that necessarily mean that it's life? You're looking for patterns, you're looking for things changing, if things are actually still alive. And there's a lot of people out there, and I'm not one of them, I will say, thinking about how to do these measurements and how to do them in situ in a super harsh environment like Europa's surface. But what I've been more interested in and focused on is, where are we going to do those measurements? Where are those ocean worlds? What are the clues that they're actually ocean worlds? And then the astrobiology people can step in and say, okay, here's how we're going to make the measurements and figure out if there's actually life there. Because then the next step is, you can do these surface measurements. And once you're measuring on the surface, you can imagine, like I was saying, dead bugs coming out of the Enceladus plumes. Because once they hit space, they're probably going to be dead, right? They're not in their nice warm ocean anymore. And same with on the European surface. It's a super harsh radiation environment. Maybe there's some bugs out there that can withstand that for some time, but mainly you're going to want to get into the ocean, right, to look for things that are actually still alive. And then we're talking about a drill or some sort of penetrator, which is, a whole new technology. Again, expensive, difficult. You don't want to kill everything by going in there, right? So it's very difficult. It's super interesting. And one of these days we're going to do it. But there's a lot of steps first. And so that's why we're thinking about kind of a big program, and kind of systematically going through and doing these things so that we get it right when we actually do that.
And I imagine that's part of the reason why we need this roadmap to ocean worlds group. We need somebody to advocate for these missions through ocean worlds or OPAG or what have you,
right,
just to convince people, because it is really hard and we need to convince people that this is worth the effort, right?
It's effort and money. And again, it's these are faraway places, and we need a program and kind of a plan to, again, kind of systematically address these questions. We can't just kind of, okay, do a mission here, a mission there. It needs to all be part of a bigger picture.
So I'm curious, this group that you're a part of that advocates for this kind of big picture mission to explore and identify ocean worlds. Does that need much advocacy? It seems like, right now space exploration is all about finding, suitable spots for life. And so I imagine that scientists and politicians alike, everyone would be like, yes, let's explore these ocean worlds. Or do you find that you actually kind of have to fight for this kind of mission?
Well, the thing is that it does require a little bit of fighting. And the thing is that there's so many neat places in the solar system to go, because, Mercury is really neat too. And Venus is awesome. And the moon is super cool. So, so yes, the ocean worlds might seem like a no-brainer to a lot of us, but there's a lot of other things to do in the solar system. And there's a relatively small pot of money. So we kind of constantly have to be doing this. Like, let's keep after this. Let's keep after this. And every year, things are a little different. There's new science results, there's new missions, there's a new administration, say, and so we've got to kind of have kind of the long vision, I think, for this.
Otherwise, they'll just keep sending stuff to Mars.
You don't seem amused by that, Tara.
I know, we like to rag on Mars all the time, but it's fine.
They've got plenty of missions.
Yeah, we know it. We've been there. So another thing that I always like to point out to people, and we wanted to ask for your opinion too, is that, by studying these ocean worlds in the outer solar system, can that help us understand the origins of water like here on Earth?
Right. That's a good question. We think about water here on Earth, and I like to think of it as, I like to think about the solar system and the evolution of the solar system, and what must have happened in the early part of the solar system to move things around, right? And you've heard of giant planet migration that might have moved water-rich bodies, like we talked about, from the outer solar system into the inner solar system, and comets moving around from the outer solar system, these water-rich bodies. Maybe comets brought water and even organics into Earth. But Earth is unique in that it's the only place with liquid water on the surface, and it's at this point in the solar system where that works. But we've got water in the frozen water in the moon's polar regions, very cold up there, and so the water is stable, and so that's a place where we can also look for clues to the historical record that is now erased from the Earth because of all of the geology that's happening on the Earth. If there was an epoch in the early solar system when water and organics were brought in to this part of the solar system, we might see a record of that in the lunar polar regions, because those cold, permanently shadowed regions really serve as a good kind of holding place for all of these volatiles that might be stable at liquid temperatures, at warmer temperatures on Earth, but in those lunar permanently shadowed regions, it's so cold that they are just stuck there. And so I like to think of those areas, maybe the Mercury polar regions, as kind of records of what happened in the past. And so if we can ever go there and find and safely kind of sample those areas, you can imagine maybe like a core sample, a clean core sample, to get like basically time versus depth. This is a super idealized version of it, but like time versus depth. And maybe you find some organics in there. Maybe you can trace back to if and when water and organics were brought to Earth. And then we also have this picture of, like I was talking about the thermal gradient, but also even through the asteroid belt, as you go out into the farther outer main belt, you've got more organics out there, more water. And what does that distribution tell us about what happened in the early solar system and how things moved around? And then you also have to think about another thing I was talking about before, which is space weathering. Because when we look at these asteroids, for instance, or any place with telescopes, or even a spacecraft by doing remote sensing, we have to consider that surface has been, eroded and weathered away. Eroded not by, by external processes. And so maybe the interior, that is really the more pristine part and really more of a relic of the early solar system, isn't really what we're seeing. We're seeing the exterior. And so how does that affect the story too? So anyway, that's a little bit of a jumbled answer to your question, but I think about these things, and there's so many factors that come into it.
So I'm curious, looking at, there's seems to be just this huge wealth of information and kind of open questions, but also hints towards worlds that might be oceans as well.
Right.
Are there any that you are personally particularly excited about, ocean worlds that, potential ocean worlds that maybe haven't been totally confirmed, but you are like, I have a good feeling about this one?
Well, one of my favorites is Triton. So Neptune's moon, right? And we, in the Ocean Worlds group, we ranked Triton as kind of our top priority candidate ocean world, where that is a logical next step. We, as part of this whole big kind of plan, we want to yes, we want to go to Europa. We've got Clipper going to Europa to investigate habitability. We've got Dragonfly going to Titan, and that's going to do habitability studies there too. But in terms of finding our next ocean world, we need to keep up kind of that line of thinking too. And Triton is probably the best candidate for that, because it does have these really remarkable hints of activity on its surface, like these plume streaks. We know that it's got some atmosphere, and this weird cantaloupe terrain that we saw in Voyager images. And so could these things be linked to some sort of liquid beneath the surface? Maybe. There's kind of a couple different camps on this, but regardless, it is an interesting body. I mean, it's a KBO that was brought in, a Kuiper Belt object brought in, and so you can actually tick a couple of boxes by doing a mission to Triton, because you're looking at a Kuiper Belt object and you're looking at a large moon and a potential ocean world. If you had I like the idea of doing a Cassini mission at Neptune. So doing a nice, thorough orbiter of the planet, lots of moon flybys, including lots of Triton flybys. And if you do enough flybys, you can figure out if a thing is an ocean world or not. Another easy way is to have an orbiter, right? Because then you can actually tease out the kind of interior structure. But even if you don't have an orbiter, if you just do multiple flybys, you can at least eventually figure out if something is an ocean world, depending on how many clues it's giving you. So I really like the idea of Triton. And some of the other Neptunian moons are interesting too. The Uranian moons are also really interesting. I think Uranus is definitely just next in line after Neptune for a Cassini-like mission. I would not actually complain too much if we did Uranus first, but then we can't do Triton. So, and then there's really interesting, Ganymede and Callisto are interesting ocean worlds because we know that there's oceans in the subsurface. But in terms of going after life, they're not as high on the list because those oceans are kind of deep under. Like there's a thick icy shell sitting over those oceans. So it could be that it's not that conducive to life. And also it's just going to be inaccessible, basically. But the other thing about the life thing is that Enceladus and Europa's oceans are thought to be potentially quite habitable because the ocean floor is in contact with a rocky surface, not another ice layer. And so that rocky ocean can provide energy and nutrients to putative life in the ocean. So that's kind of why those are kind of the favorite ocean worlds for going after life. Plus they're more accessible because the icy shells are thinner. But in terms of our next candidate world that we ought to go for, in my mind, it's Triton.
I'm with you. I agree. I think it's super exciting. So the last thing that we always like to ask people when they come and chat with us is, how did you sort of get to where you are today? Did you start off loving space from a little kid, or is this something that kind of grew on you? How did you get to here?
Yeah, I'm one of the people who I've always loved space. And it was kind of, when I was a kid, it probably I don't know how old I was when it started, but I've always kind of been interested in kind of space in general. And I couldn't really ever define, like what I wanted to be, but I definitely wanted to be an astronaut. That would have been good. But then as I started getting into school, and I studied engineering in college as a grad student, but then as a grad student, I got into planetary science at CU. And that's when I kind of thought, okay, this is what I've been kind of looking for this whole time. And so that was, again, I feel very fortunate to have kind of stumbled into that. And also to be at CU, where they've got this fabulous kind of capability for doing spacecraft missions and building instruments and so forth. And so that was really perfect. But ever since, grad school, when I was working on the Galileo mission, and then I got involved in the Cassini mission after that, that's been, the place for me. I feel super fortunate to be one of those people who I love my job. So.
So now we have a little segment that we like to do called Capcom Q&A. These are listener submitted questions, right? Capcom, like the space, Yeah. And I also would like to remind anybody listening right now to please send us your questions. You can at colorado.edu/Fisk. Anyone can send in questions anytime. Doesn't have to be targeted towards any specific episode, but please go ahead and if you have questions, let us know. We'll pass them on to our guests. And who knows, if we get enough questions in one area, maybe we'll seek out someone that is specific to that spot. So anyways, now that I've plugged our little segment there, our first question comes from Stephen in Arvada, who's asking, how do we find out or know what's underneath the ice?
Oh, good question. Right, because all of these ocean worlds in the outer solar system are covered by ice. But we look for clues that there is liquid under there. And a clue might come in the form of a plume, like we see at Enceladus and maybe even at Europa. And it might come in the form of like tectonic activity, kind of like cracks, maybe cracks in the ice. This is what we see on Europa. We see these chaos regions where their ice looks like it's been broken up, where it's maybe even like icebergs relatively recently floating on the surface. That makes you think, okay, is this ice sitting on top of something mobile, like water? We look for hot spots. If there's an energy source, something hot under the ice, it might be heating up the water and heating up the ice and appearing as a hot spot. We might see an atmosphere, either a localized atmosphere or a global atmosphere, which might mean that there is outgassing of some sort. You don't have to have outgassing, but that is a clue, a potential clue. And then also you might look for an induced magnetic field like we had at Europa. That's another kind of clue that we look for that there's liquid underneath that ice. Those are some of the things that come to mind.
And of course, Enceladus is like it's literally shooting water out at us. Thank you.
Right. Enceladus, like I said, makes it very easy for us to figure out something is going on there.
So our other question that we got from Christine from Boulder is asking, do you still want to be an astronaut, and would you go to an ocean world if it was feasible?
Oh, okay. Well, you don't get me started. I would still be an astronaut. I think it would be a hoot to fly in space. I would love to work on a space mission. I think working as part of a team to do some of those experiments and would be really fun. That would be great. I think that personally, for me, my only hesitancy at this point is that, I know that the astronaut job is full-time. And so it would be hard for me to continue with my planetary science research and be an astronaut. So that would be a trade for me. But flying in space would be totally awesome. And I'd love to go to space station. I would like to go to an ocean world with a few caveats. My favorite ocean world, I didn't even get into this, but I can say a little blurb, that my favorite ocean world in the solar system for humans is Titan. Because remember, we started saying at the beginning of the segment that very few of these moons have atmospheres, but Titan does. Titan has actually a properly thick atmosphere. And in a lot of ways, it's the most Earth-like place in the solar system. So I think if humans could actually get there in a timely manner and not get, completely irradiated in the journey there, once they got there, they would be safe in a lot of ways, because there's no radiation coming to the surface, because it all gets absorbed by the atmosphere. Really, Titan is the best place for humans to live if you can figure out a way to withstand the cold and so forth. And even in terms of resources, there's energy to burn, as they like to say there, in the form of all those hydrocarbons.
Awesome. Well, Dr. Amanda Hendrix, thank you so much for joining us today on this episode of A View from Earth. It has been such a pleasure to learn about ocean worlds with you.
Well, it's been fun talking with you. Thanks for having me.
Well, everyone, thank you again so much for joining us. And thanks to Dr. Amanda Hendrix for coming and talking to us about ocean worlds, a subject that is very near and dear to my own heart. We're super excited for you guys to listen, and be sure to come back next week. We are having a really interesting conversation with Dr. Heather Demarest, who studies the philosophy of science and how science interacts with our brain and how our brain views science. And also, it gets super weird. You're going to love it. I promise. It's really cool. Also, be sure to check out our website, www.colorado.edu/FISC. There you can do all sorts of cool things, including look at our schedule of upcoming guests. You can submit questions for Capcom Q&A, where we can pass your questions on to our experts. It also gives you a chance to donate if you would like to hear more of our podcast and help us keep going through this wacky, crazy COVID times. We would love your donations and support from listeners like you. You can find us, as always, on YouTube, Spotify, SoundCloud, and Apple Podcasts. So be sure to comment and like and subscribe so you don't miss any of our upcoming episodes. And hopefully we will see you next week.